Okay, so we're now moving on to some SPSS examples of correlation. And we're going back to the Fear of Statistics data set that you know and love. So again, you can open this in SPSS by just in Windows double clicking on the data file, or from within SPSS go File Open Data, and then you can list all the data files in the directory. And here are all the SPSS files that I've been using for this class. Okay, so just kind of a quick reminder of this data. This is all about people taking stats and math classes. We have some kind of demographic information about them, their gender, their major, why they're taking this class, how hard. We also have stuff like how hard the exams they're given are. Stuff that if I try to experiment with you in class by giving you different hardness of exams, you probably wouldn't take it very well. Things like the amount of caffeine, some scale about how phobic you are, statistics, how many previous math classes you've actually took, your results on maths and stats exams in the class, and then some measures of things like heart rate, your base heart rate directly before you take an exam, directly after your exam, and also some measure of anxiety as well. So what we want to do now is we want to just look for kind of correlations and see how these variables are actually correlated with each other. So the first thing we're going to do is we're actually going to do what we did in chapter 10 is we're going to build kind of the matrix scatter plot. Whoops, we didn't want to do that. So we want to go to basically go to graphs, chart builder, and we want to go to the scatter diagram, and then we want to go to kind of the matrix scatter plot here. And what we're going to do is we're going to kind of click 5 different variables. So we're going to actually look at your math quiz score. We're going to look at your 2 of your heart rate measures. And we're going to look at 2 of your anxiety measures. So exactly the same as we did in chapter 10. And we're just going to drag those to the scatter matrix area where you choose your variables, and we're going to click OK. And we can see the scatter matrix. So basically, kind of relate this now to the material we've done in class. If you look at the heart rate base and math quiz, it seems almost to be a cloud, so there's probably very low correlation here. But if we look at the anxiety measures, the base, and say anxiety pre, there seems to be this kind of correlational pattern. And it makes sense, some people are generally more anxious than other people. And, there may be differences before an exam and normally, but, there should be some kind of correlation between the 2 measures. And again, as per chapter 10, you can actually click on them and draw a little line that actually gives you kind of the direction of the relationship as well, if you want to help out. So okay, so what we're going to do now is we've looked at the things visually. Now we're actually going to kind of calculate some actual correlations using SPSS. And what we're going to do is we're going to let's go back to our thing. Let's go to Analyze, Correlate, Bivariate. Now, bivariate just means we're comparing 2 variables at a time, by 2. So we're doing comparisons of 2 variables. Now, we're going to pick exactly the same variables that we did before. So we're going to pick the math quiz, the heart rate pre, and the heart rate base and the heart rate pre, and the anxiety base and the anxiety pre. We're going to actually choose the Pearson correlation and the Spearman correlation. I'll talk a little bit about that in a minute. And we're going to do a 2-tailed test of significance. Again, we'll talk about the significance tests. And we're going to flag significant correlation. And we're going to click OK. So you have a table here. And each entry in a table is the correlation between 2 variables. Now you note that of each entry, the top value is the correlation, The next one is the significance, the p-value. And the third one is the n, or the number of comparisons, just in case you have, some of these have a little bit of missing data. So for example, some of the students, 15 of the students don't have a math quiz score. So let's have a look. Why are these variables actually just all one? Well, that's because, you know, when we talked about perfect correlation, I said a variable perfectly correlated is correlated with itself. So math quiz is perfectly correlated with itself. So is heart rate base. Now let's have a look at perhaps some other kind of correlations, some that are not exactly perfect. So let's have a look at the correlation between the math quiz and the heart rate pre. So let's go back to our Pearson here. We've got the Pearson and the Spearman. So let's go to the Spearman and let's go to the heart rate pre and the math quiz. So let's go down. We can see it's a negative correlation, minus 0.224. It's got a p-value of 0.039. And these tests are like all the other tests we've done over the last few weeks. The p-value, the lower the p-value, the more likely you are to reject the null hypothesis. So we have the significance on the second row. The null hypothesis is there's no correlation. The correlation is equal to 0. And the alternative hypothesis is there is some correlation, it's not equal to 0. And we look here, and then we say minus 0.224 and a p-value of 0.039. Now look at the correlation between heart rate pre and heart rate base. This is like really, really high, which you could imagine it should be. It's very significant because people generally have high or low heart rate. So the correlation is 0.483, and we can actually see the significance is 0.000. The previous one was like mildly significant. And we can see there is some relationship between heart rate pre and math quiz. This negative relationship. If you have a really high jittery heart rate before the exam, then you're likely to do worse on the math quiz. But it's not that strong a correlation. Now these are the Pearsons. The next one is the Spearman. Now the difference is Pearson correlation's designed for kind of continuous variables, for like ratio and kind of interval scale data. So if you have things like, you know, the time it takes for somebody to go around a shopping center and, you know, how far they are from home, a distance, then those are all continuous. If you have results from like your Likert scale questionnaires, like a scale of really dislike to really strongly like, you have ordinal data, so you may want to use the Spearman correlation. But the fact is it gets mixed up a little bit. A lot of people for ordinal data use Pearson correlations, but the advice is to use the Spearman correlation if you've got ordinal data. But they have very similar values. In this case, the Spearman correlations are a little bit stronger. So the heart rate pre and math quiz is minus 0.255, and the p-value is a little bit lower, and the correlation between the two heart rates is just over 0.5. So depending on your data, if you're using Likert scale data, it's sometimes a matter of personal preference. But just know that the Spearman is going to be out there. Okay, so let's go back to the slides. Okay, a few other things. Something we're not going to emphasize too much, particularly we'll talk about it a little bit more when we do regression. That's the coefficient of determination. That's just kind of a non-signed version of the strength of relationship. And when we go to regression, we'll talk about how it's related to the variance. So the amount of variation in one variable explained by the other is the coefficient of determination. So say we had a correlation of 0.4. Then the R squared is going to be 0.4 times 0.4 is 0.16. And let's just say we have an R of minus 0.4. Then we'll have an R squared, again, of 0.16 because it's not regression. It's not directional. And again, you know, if we had an R squared for our tweet rate versus movie revenue, and it was say 0.3 or 0.5, we could say, like, if it's 0.5, we could say 50% of the variation in the movie revenue is accounted for by the social media buzz or the tweet rate. So this is actually quite important when we get to regression. Okay, so we talked about the Spearman correlation, and now we get to the actual statistical test. So imagine, let's just have three different, let's just kind of get a bit of notation first. So R is my sample correlation. So we get a sample of data, we calculate R. So if we were doing if we were doing a standard hypothesis test, this would take the place of the X bar. It's not the same thing, but it's a sample. And this lovely thing called rho is the population correlation. We're making inference about what it is in the population. So again, if we were doing a normal hypothesis test, this would be in place of the mu. So you get the idea. We're using the sample to make inference on the actual population. So let's go all the way down to the bottom, and let's just draw a little scenario. So we've got two variables, and they're kind of really strongly correlated. Yeah, there's obviously this big correlation between X and Y. Then we're going to probably say we have our null hypothesis always that the population is, the correlation is 0. And what we're trying to prove is that the correlation here is greater than 0. And in this case, yes, this looks like we have this positive correlation. We've got a strong slope, and it's all about the slope relative to the error. We have a strong slope relative to the error. Now, let's just do the opposite example, and we have this really strong negative correlation. My null hypothesis is that the correlation is 0. And my alternative hypothesis is that my correlation is less than 0. And again, this looks like a pretty strong relationship. At least it would be if I could draw properly. These all should be close to the line. And so we're going to say yes, that this is probably a significant relationship. Now imagine that we have, again, this scenario here with this big cloud and there doesn't appear to be any relationship. You see, we've got lots of error, and we probably have a really straight line here. You know, this is indicating, yeah, where we had null hypothesis. Or let's just do a two-tailed one. It's not equal to 0. And we're probably going to fail to reject. We've got no evidence here. So we've got, in this instance, the correlation is probably closer to 0. Okay, let's go back to the other end. Okay, now let's just think a little bit about this. You don't have to this class, and I put not on the exam, but by that I mean you don't have to know the statistics. You do need to know, I might actually remove that just so there's no confusion. You do have to actually know the hypotheses. So let's just think that we have basically what this T does is it converts the correlation into a T statistic. And we're not going to go through them up, but, you know, it's just basically a scaled version of R. And it's actually, again, a bit beyond what we're doing in this class, but it's actually equivalent to the test for a univariate regression. It's the same, it'll always give you the same value. So basically, the bigger the T, the more positive significant it is. So as this kind of goes up, my T gets bigger. And as we get below 0, my T becomes smaller. So again, this is a very standard T-test. And we can look in one direction with a one-tailed test, or we could look in both directions with a two-tailed test. So let's just do a one-tailed test. Again, we convert this into a t. We've got my type 1 error here, my alpha. And again, this is just, we kind of start off with a t at 0, which is equivalent to a, okay, I don't know what happened there. Okay, so it's very sensitive, this pen, as you probably realized. So we started off with t equals 0, which is equivalent to, okay, I've got big clumsy fingers. I think I've gone too close to the bottom of the screen. So we have a t equals 0, which is equivalent to a rho. Let's just draw it on the whiteboard. Okay, this is much better. So we have t equals 0, which is equivalent, you know, in your sample to your r being equal to 0. And let's just have my null hypothesis here. My null hypothesis is that my correlation is 0. My alternative hypothesis is my correlation is greater than 0. And, you know, this is going to be my rejection region here. So this is going to be my T star, which is an alpha. The degrees of freedom for this one is n-2, but again, don't worry about it for this class. So as my correlation, as my R gets bigger, my T gets bigger, and it gets bigger and bigger and bigger and bigger and bigger until I eventually reject. So we're going to reject if my T is greater than T alpha. But imagine we're here. So imagine this is my T. This is going to be the area more extreme. This is my P value. So again, we go right until we hit this variable and it's got my alpha to the right. So this is of area alpha. And so we're also going to reject if my p-value is less than alpha. So it's exactly the same as a normal t-test. If my p-value is less than alpha, I've got evidence for this. So again, imagine we had a t-value here, then my alpha would be much small. My p-value would be much smaller than my alpha, so I'd reject. So we can actually do it the same for the other way around. So we have my rho equals 0, and HA, we have my rho is less than 0. And again, this is my T equals 0, and it's also my R equals 0. So as my correlation gets lower, again, let's just have my alpha here. And so as my correlation gets lower and lower and lower, until negatively lower and lower, until I hit this, and then I reject. So this is going to be my T minus alpha. Sorry, this will be minus T alpha with n-2 degrees of freedom. So we're going to reject H0 if my T is less than minus T alpha with n-2 degrees of freedom. And again, exactly the same with the p-value. Imagine we have my T here, maybe say a T is -1 or something. It's not big enough to be significant. But again, as we get lower and lower, lower and lower, we hit this significant, and eventually we're going to reject. So we're also going to reject H0 if my P is less than alpha. So lovely. Again, all these tests with SPSS, you don't have to worry about your T statistics or whatever. You're just rejecting if the P is less than alpha. And again, let's go. I think we can fit it on here. Let's go for the final thing. So H0, we're equal to 0, and the alternative hypothesis is not equal to 0. And then we've got the alpha over 2. And we got the alpha over 2. And again, we're checking in both directions. So we're checking for a positive or a negative. So if we go this way and hit the boundary, if we have too big a T, we reject. And if we have too small a T, we reject. And so this would be T alpha over 2. And again, with n minus 2 degrees of freedom, which we don't have to worry about for this class, and minus T alpha over 2. And we're going to reject if the absolute value of T is greater than T alpha over 2 with n minus 2 degrees of freedom. And again, the P value is on both sides. So this is my p-value, because again, if we're doing it on both sides with the alpha, we have to have the same on the p-values. It's all values more extreme. So that's p over 2, and that's p over 2. And so we're going to reject, again, if p is less than alpha. Now notice again, SPSS is two-tailed. And it gives you kind of both p-value on both sides. So if you want for one-tailed, you need to divide it by 2. And I'll like double and triple exclamation mark that. Okay, so we'll just go kind of, now we've done that, we'll just kind of go back to the slides and we'll go back through that output from SP. Okay, so again, here now we're just doing what we looked at before. We're saying, is the math quiz correlated to HRP? We set the alpha equals 0.05. This is standard type 1 error, average strictness test. We're going to do a two-tailed test. My null hypothesis is that my population correlation is 0. The alternative is not equal to 0. So we're looking for evidence that it's not equal to 0. And we'll say my p-value is 0.039. It's less than my alpha. So we reject 0. So there is some evidence that we can reject H0, and this correlation is significantly different from 0. And we could have done this with we could have done this with a one-tailed lower, and all we would have done is we'd have divided this p-value by 2. Okay, so that's it for correlation. And what we're going to do is next kind of little video, we're going to start looking at regression and